So much of what we say at the beginning here is just going to be stuff that you already know very well. For example, we call this a primary amine, where there's one alkyl group. We call this a secondary amine, and we call this a tertiary amine. All right, you've seen that before. Amines, their chemistry is dominated by the nitrogen with the lone pair on it. Amines are bases, as you know. In general, their conjugate acids have pKa's in the range of 9 to 11. So at physiological pH, you expect amines to be protonated and be positively charged. And whether or not an amine is protonated or positively charged can change its physical properties. We'll call the amine that has the lone pair on it the free base, and the amine that is protonated we will call, usually there's a counter ion, we'll call that the ammonium salt. And a lot of free bases are not that soluble in water, whereas the ammonium salts are. And this has a lot to do with drug formulation. So often if you see for various medications, as I explained earlier when we talked about sertraline, which is an amine, some medications will have hydrochloride in the name, and that really means it's an ammonium salt. They've added HCl to protonate the amine, and then the chloride is the counter ion. It's the ammonium salt, and that's crystalline and more solid than the free base form is. Another interesting thing about amines is they tend to smell bad. So try methylamine. If there were 3 methyl groups, that's one that smells kind of like fish. And so the bad smell associated with rotting fish or fish in general, something smells fishy, what you're smelling is amines. So this is one reason why you may have noticed if you go have seafood, there's always lemons nearby, right? We went to, oh goodness, a couple of years ago, we go down to St. George over New Year's with some of my family, and my brothers-in-law were like, dude, let's go to Mesquite and go to a buffet at the casino there. They have prime rib and crab. Prime rib seems kind of fatty to me, so I'm not a fan, and crab's like, eh. So I'm sitting in the casino, and they've got these big piles of crab legs and molten butter to dip it in, and there's lemons everywhere. Do you know what the lemons are for? Well, I mean, traditionally, let's put lemon juice on something, it'll make it taste good. Yes, and the thing that smells like fish stink is an amine. Lemons have citric acid, which is a carboxylic acid. So what do you think the acid does to the amine? Protonates it, turns it into the ammonium salt, then it's less volatile, it doesn't smell as bad. So you want to do this experiment, go buy some salmon or halibut, or go get a carp from Utah Lake if you want. Wrap it in foil, stick it in your trunk for several days, smell it, and then put lemon juice on it and smell it again. And you'll see that the lemon juice does help with the bad smell. I'm not extra credit. Bring me a rotten fish. Yeah, sure. Got one right here. Always be prepared, yeah. Okay, so one of the things that's kind of fun to do with amines is rank them in terms of basicity. And there's 2 ways to do this. For amine basicity, you can consider stabilization of the lone pairs, of the lone pair electrons on nitrogen. So things like resonance or aromaticity would tend to lower the energy of an amine and make it less basic. The other thing you can do is consider the stability of the conjugate acid where a more stable acid would be associated with a more basic amine. So I'll give you a couple examples of this. If you were to compare this alkylamine, ethylamine, with aniline, aniline is the aminobenzene, you would see that the ethylamine is more basic, meaning a stronger, more reactive base, whereas aniline is less basic. And the reason for that is this lone pair is highly localized. It's not delocalized by resonance, whereas that lone pair is resonance stabilized. And you can tell that it's resonance stabilized with the ring because you could draw a resonance structure where that negative charge would be on this carbon or that carbon or that carbon. So delocalization is a stabilizing thing. And so you can use that to rationalize why some amines might be more or less basic than others. Even among anilines, you can do things that might lower or decrease or increase the basicity of the aniline. So let's just redraw aniline here. Then let's say we put an electron withdrawing group on the ring versus an electron donating group on the ring. So compared to aniline, and remember, you're thinking anything that would tend to spread out the lone pairs. The lone pair electrons on the nitrogen should make the molecule less basic. So what do you predict the nitro group should do? Should that be more or less basic than aniline? Okay, less. And the reason why is this resonance structure, which I'll draw below. We'll use the double-headed arrow. I'm going to actually draw out the nitro-Lewis structure so you can see, how this is. All right. Those are the arrows to convert one aniline resonance structure to another. And you can see that the presence of the nitro group as an electron withdrawing group has the effect of providing additional places for the lone pair on aniline to be delocalized. And so you would predict that that electron withdrawing group would lower the electron richness of the benzene ring, which would make it even more favorable for the lone pairs on the nitrogen to donate into the ring. What do you predict the effect of an alkyl group should be? What kind of group is an alkyl group? It's donating, it's not a resonance donor, but it is a donating group. What do you predict that does to the lone pair? Should destabilize it, right? If you make the benzene ring more electron rich, that makes it less willing to accept electrons from the aniline. A more electron rich benzene is less able to accept the lone pairs from aniline by resonance. So you predict this one would be more basic than just regular aniline. So you can use that kind of reasoning to work your way through. Yeah?
Would we treat halogens as electron donating or withdrawing?
Oh, that's interesting. I don't know. I need to look at the pKa numbers. I would predict that for halogens, electronegativity would matter more. Yeah. You can use a similar rationale for comparing an alkyl amine versus an amide. right? Lone pairs that are, again, resonance stabilized because they're adjacent to a carbonyl are lower in energy. And amides are not very basic, where this alkylamine is basic. And you saw this played a role in something we talked about over the past couple of lectures. Remember that we said that having a nitrogen, an amino group on a benzene ring interferes with the Friedel-Crafts reaction because you don't get the desired product because the lone pair on the aniline is reactive enough to attack the Lewis acid, and you get this weird Lewis acid, Lewis base complex between the nitrogen and the aluminum. And the workaround, we said, was to convert the aniline into an amide, because then the lone pairs aren't a problem. They're less reactive now, stabilized by resonance. They won't react with the Lewis acid aluminum chloride, and you can go ahead and do the electrophilic aromatic substitution reaction that we talked about, getting here both ortho and para products. So this, the idea of stabilizing a lone pair by resonance has consequences, and you can use it to avoid reactivity problems. All right, questions so far? Mostly not new stuff. The other thing you can do is use the concepts of aromaticity to sort of judge the basicity of various lone pairs. Something on your most recent problem set that you did in preparation for the exam was to look at this molecule imidazole. And I think we talked about this in class too. But you could look in the molecule itself and ask which nitrogen is most basic. And that's the same as asking which nitrogen, which lone pairs are highest in energy. And at the same time, that's the same question as asking which conjugate acid is most stable. The most stable conjugate acid will come from the most reactive base. So we could draw conjugate acids where we protonate on the nitrogen on the left to get this conjugate acid. And then we could draw the separate conjugate acid where we protonate on the nitrogen on the right to get that conjugate acid. So we can reason through this either way. Let's start with which conjugate acid is most stable. Take a look at those. They're both positively charged, but there is a clear difference. What is it? What's wrong with the one on the left? Is it aromatic? No. Why not? It's not actually anti-aromatic either. It's got a sp3 atom. So this is a nitrogen bonded to 4 things. So this is no longer fully conjugated. So it's just flat out neither aromatic nor anti-aromatic. This one is, we count 2, 4, and 6 electrons. Now, how do I know to count those? Again, you have to have learned something about what happens for lone pairs adjacent to pi bonds. Some of you are looking at that and saying, oh, that nitrogen should be sp3 hybridized. The reason you're doing that is because you've looked at alkylamines before and said, hey, that nitrogen's surrounded by 4 groups, ought to be roughly sp3 hybridized, and the lone pair should be in an sp3 orbital. And that's true unless there's an adjacent pi bond, in which case the lone pair will be stabilized by resonance and the lone pair will be in a p orbital. The best way to see that is to actually draw the other resonance structure, where you move the lone pair from the nitrogen to form a pi bond here, and then move that pi bond out onto the other nitrogen as a lone pair. And that allows you to see, first, that the lone pair is participating in resonance. Second, it allows you to make the conclusion that that nitrogen has to be sp2 hybridized. If it's sp2 hybridized in one resonance structure, it will be in the other as well. Okay? So when you see a nitrogen adjacent to a pi bond, and that nitrogen isn't already in a pi bond, then the conclusion is that the lone pair is in a p orbital where it can participate in resonance. So we do count that. So this is aromatic, and the cation is also resonance stabilized, right? The positive charge is simultaneously delocalized on both nitrogens, whereas it's entirely localized here. So you could conclude that this one is the more stable conjugate acid. And that would automatically tell you that this nitrogen is the more basic nitrogen. Okay? So that's one way of approaching the question. Draw the conjugate acids, decide which one is more stable. The second way is to just look at the base and say which lone pair is more stable. Similar reasoning here. You would need to look at this nitrogen and come to the same conclusion as we did over to the right, that lone pair is in a p orbital, that it is resonance stabilized, and that it is part of the aromatic pi system. In contrast, you would conclude that that lone pair is in what kind of orbital? sp2. How do you know it's not p? Because that nitrogen's sp2 hybridized, so there's a p orbital somewhere, but how do you know it's not the lone pair? Yeah, because the nitrogen's already in a pi bond, the lone pair is already spoken for. So we would still count this molecule as aromatic. The lone pairs that count for aromaticity is this one and then those 2 pi bonds. But the one in the sp2 orbital is not part of the pi system. In fact, it is perpendicular with the pi system. It's housed in the plane of those sigma bonds. It's not part of resonance. So we would conclude that the lone pair on the pink lone pair is more stable because this lone pair is localized and not part of the pi bond, not part of the pi system. So higher in energy, therefore more basic. Okay. Questions about that reasoning? Okay, another another way you can look at amine basicity is using a concept really from 351. Two types of lone pairs. Both of these lone pairs are localized lone pairs. This one is in an sp3 type orbital. This one is in an sp2 type orbital. Now, you learned a concept in 351 about hybridization, where you learned that the more percent S character a hybrid orbital has, the lower in energy that hybrid orbital is. And it's just averaging, honestly. Remember, s orbitals are a little bit lower in energy than p orbitals. So an sp3 orbital, which is 25% s, and an sp2 orbital, which is 33% s, which one should be more stable? One on the right, sp2. More s character. More s means more stable. Ooh, that works out nicely. Nice mnemonic device. S is for stable. So if it's more stable, you would predict that this would be less basic. And indeed, if we look at the conjugate acids, there's a pretty dramatic difference in acidity. The ammonium ion for the alkyl amine has a pKa of around 11.1. For the conjugate acid of this molecule here, which is called pyridine, the pKa of the corresponding pyridinium ion is around 5. So much more acidic because the conjugate base is much more stable. Okay. And just remember, you can approach this problem, you can approach questions of relative basicity either by comparing the stability of the lone pairs that are going to act as bases, or by comparing the stability of the conjugate acids. But you've got to remember that a more stable conjugate base is associated with a stronger, more reactive acid, and a stronger, more reactive base is associated with a weaker, less reactive acid. All right. What I want to do now is just talk a little bit about some interesting amines. I'm doing this because there are a lot of amines that are used as drugs, and some of you aspire to prescribe medications to other humans at some point in your life. So maybe it's useful to have at least some idea of what some of these medications are. And some of the medications mimic biological molecules. For example, when you're nervous, sometimes your body secretes this molecule, which is adrenaline. I'm not sure whether you go into the testing center full of adrenaline or not, but if you do, then this is what's being made. And there's a related molecule that's also made called noradrenaline. And that's the same as adrenaline, it just lacks the methyl group on one of the nitrogens. So noradrenaline is a primary amine, whereas regular adrenaline is a secondary amine. And there are molecules that are related to these structures and sometimes have similar biological effects. For example, if you look at this one, it's got the same basic phenyl group, ethyl group, and nitrogen that the adrenaline and noradrenaline have. Do you see? I'll sort of highlight the core structure: benzene ring, ethyl group, and nitrogen. So this molecule has that too. One difference is it has a stereocenter here that the others don't. And then there's a methyl group on the nitrogen. And this is methamphetamine. So you can see some of the structural similarities, and you could imagine related structure might lead to sort of related biological activity, though there are some differences. Other amines that we've talked about include neurotransmitters. We did a bunch of stuff when we talked about biological decarboxylation, where we said, hey, the amino acid tryptophan, which has this amino-containing side chain that's called an indole, and then has a nitrogen here and a carboxylic acid here. We said that this is the amino acid tryptophan, can undergo a biological decarboxylation reaction mediated by the cofactor PLP, and we lose CO2, and afterwards what's left is still the indole ring, and then we lost the carboxylate group, but the nitrogen's still there, and this amine is serotonin. So we talked about that, along with dopamine and histamine and some others. And we talked about how some of the serotonin selective serotonin reuptake inhibitors are also amines. So a few of these SSRIs that I'll show you include Prozac, which you're going to see also has the same benzene ring that some of these other amine-containing drugs have. Not exactly the same pattern, but there's the amine, and then on this carbon's an oxygen with another benzene ring and a trifluoromethyl group. So that's Prozac, and then sertraline I've already drawn for you. You got chloros on the rings, stereocenter here, 6-membered ring. The nitrogen branches off here. I'm drawing it for you in the free base form, but as I said, it's probably sold and packaged as the hydrochloride salt. And this is, the trade name was Zoloft for sertraline. Anyway, amines are present in a lot of drug molecules, and their chemistry influences a lot of their physical properties. All right, so now we want to do a little bit of chemistry. We want to talk about how to do some amine synthesis. And the first thing that comes to mind when thinking about amine synthesis is, why don't I just start with like ammonia, and why don't I do an SN2 reaction? That looks good. And then I could convert the ammonia into this ethylamine. All right, just simply via SN2 attack of the bromide, and then presumably I would make this ammonium ion intermediate, which Br minus could deprotonate, and that would give me my amine. And that looks good on paper, but there's a problem, and that is that you've learned that alkyl groups are electron donating. So the electron donating alkyl group increases the basicity of the lone pair on the nitrogen. Having a withdrawing group would lower the energy of the lone pair. Having a donating group increases the energy of the lone pair, which means the molecule here is more reactive, more basic, and more nucleophilic. Basicity and nucleophilicity are almost the same thing. Basicity is related to how likely is it to attack a hydrogen. Nucleophilicity is how likely is it to attack a carbon or another electrophile. So a higher energy lone pair should be both a better base and a better nucleophile. And if your starting material if your product is more reactive, has more nucleophilicity than your original molecule, then your product starts to compete with your original molecule for the remaining reagent. And so what you tend to see when attempting to do an SN2 synthesis of an amine is over alkylation. You can actually even make the quaternary ammonium salt. And it's difficult to do this in a controlled way. And a nice hypothesis is, well, could I just add one equivalent of the alkyl halide? And the answer is sometimes it doesn't work well and you still see a mixture of products. So we need a new solution. We need an alternative for making primary amines. Of course, if your goal is to make a quaternary ammonium salt or even a tertiary amine, you may be good to go. But if it's not, if you just want a primary amine, you need a workaround. So we're going to introduce something that's called the Gabriel synthesis of primary amines. And this is kind of cute. I mean, probably not that cute. The idea is you're going to use a molecule where the lone pairs are not really that reactive. The lone pairs on the nitrogen are not really that reactive, okay? So this molecule is called phthalimide, and it's almost unpronounceable. I'm not sure what language the PH, TH together comes from. I'm not sure if you're supposed to go and then I think most people just say phthalimide and call it good. I think the PH is silent. So whatever. But phthalimide, if you look at it, the lone pairs on the nitrogen are really not reactive because they are resonance stabilized. So that's going to help us avoid over-alkylation. The other interesting thing about phthalimide is that the pKa of this proton is 10 because the conjugate base is stabilized by resonance. I'm going to draw that conjugate base for you. OH minus removes the proton on phthalimide, and you get the following conjugate base as a result. That nitrogen has 2 lone pairs on it and is negatively charged, but you can see that that negative charge is stabilized by resonance, right? I could draw, I'll just draw one of those 2 resonance structures to show you. And of course, we could put the negative charge on the other oxygen too. So the anion is resonance stabilized, meaning it was easy to remove the proton. Now, the anion, because it is negatively charged, is a nucleophile. And so once you've made the anion, you introduce your alkyl halide. And what happens here is a simple SN2 reaction in which the nitrogen attacks the carbon that bears the leaving group leaves, and there's the leaving group, and you end up with one and only one alkyl group. And the reason that a second alkyl group doesn't go on is, again, because the lone pair on that nitrogen is resonance stabilized with those carbonyls. It's an amide on either side. Okay, so with that, once we're there, you can add a strong base in the presence of water, and the reaction that happens here is called amide hydrolysis. Amide hydrolysis is usually really slow. It's faster here because if a nucleophile were to attack at this carbonyl carbon, and we would get a tetrahedral intermediate. I'm not going to draw the mechanism, though I'll show you one of those tetrahedral intermediates so we can think our way through it. Here's the tetrahedral intermediate you would get if hydroxide attacked the carbonyl carbon. Normally, we wouldn't think of a nitrogen as a good leaving group because, of course, negatively charged nitrogens are pretty unstable unless they're stabilized by resonance. What can happen here is that the pink oxygen can act as a kicker-offer to kick off the nitrogen leaving group. And you'll see when I draw what it looks like that it's resonance stabilized. That one of the lone pairs on the nitrogen can be on that oxygen. And in any case, right away, right nearby, is an OH group, which the nitrogen can protonate on. Anyway, you do that twice, and you release this dicarboxylate, which isn't your desired product. Your desired product is the alkylamine. Okay? So this Gabriel synthesis is a great way to make primary amines via an SN2 type reaction, but with no risk of overalkylation. And though amides don't usually hydrolyze very well, this is a chapter 16 reaction, they do in this case because of what I showed you here. When the nitrogen leaves, it's a good leaving group, and you have, because it's resonance stabilized, and you have in any case an acid right nearby to protonate it. All right, other questions?
What's stabilizing it the second time?
Good question. What's stabilizing it the second time? And so you're saying, what if we had this? How is that going to leave? And I agree that this is a terrible leaving group. It either gets protonated first or it gets protonated while it's leaving, possibly by this OH group. Yep. All right, one more synthetic strategy for amines. This one is not going to be new. It's a review of something you already know, and that's reductive amination. We learned this at the very beginning of the semester in, I think, chapter 14, when we learned about imine formation. So you know, as an example, that you could take an aldehyde or a ketone and react it with an amine. You need an acid catalyst. Generally, you need to be removing water for this process, so you don't want to use hydronium as a catalyst. Instead, you want to use some organic acid, for example, a carboxylic acid. And that will first form an imine, which looks like this. And then, so that's imine formation, step one. Step two is reduction, and you can use a reagent like sodium borohydride. There's another reagent that I'm not sure your text introduced or not. It's a version of sodium borohydride that has a cyanide group on the boron. That's sort of an electron withdrawing group, and so Cyanoborohydride is less reactive than sodium borohydride. Both of them are okay in reductive amination reactions. This happens in a protic solvent because both sodium borohydride and sodium cyanoborohydride are totally fine in protic solvent. You deliver a hydride to the carbonyl carbon, and the nitrogen gets protonated, and your product is this. And in the past, we focused mostly on the carbonyl carbon. Today, we're focusing on the amine. Notice that what we've made is a new carbon-carbon bond. The effect of this reaction is to make a new carbon-carbon bond on the nitrogen, again, with no risk of over-alkylation. So you will see people doing this reaction and you'd be like, why didn't you just do the SN2 reaction? That's so much easier. The answer is it doesn't work. You get over-alkylation, but reductive amination is a way to get secondary amines without risk of over-alkylating. Okay? Well, that was fun. You're still here. You didn't walk out in the middle. You're welcome to, by the way, whenever. What I want to do now is to set up something we're going to do next time, and that is I need to tell you a story about sort of the birth of the modern chemical industry. And the story starts in England when a young man by the name of William Perkin was working in his lab, which was in his house. And Perkin was trying to make an anti-malarial drug called quinine, and he was using aniline to do it. What he didn't know at the time was that his aniline sample was contaminated with two derivatives of aniline with alkyl groups on it, ortho and para-toluidine, which is the name for the aniline that has methyl groups in the ortho and para positions. This was the 1850s, and at the time, the methods for separating molecules from each other were probably mostly related to distillation, where you heat up a solution of a molecule and they evaporate at different rates, and then you collect them in a container that's colder, and they condense on the inside of that container. So it's no surprise that he wasn't able to separate these three molecules. But he was trying to make quinine, and he was doing it with an oxidizing agent. Now, remember, again, it's the 1850s. Not a lot is known as much as we know now about the reaction. So this seemed like a reasonable thing to try. In retrospect, there was no way he was making this quinine molecule via this method. And so this is potassium dichromate. You may have seen that reagent before in 351. It does oxidizing chemistry. It will oxidize primary alcohols to carboxylic acids. So it's unclear what he thought was going to happen with the amine. In any case, he got a round bottom flask he got his flask that had this dark, chunky, black, insoluble solid at the bottom of it. Now, usually that means a failed reaction, and some of us would just throw the flask away at that point and try again. He made the interesting decision to try to clean the flask out, started rinsing it with alcohol, and though the solid didn't dissolve, the alcohol that he put in, ethanol, was purple. And he thought, ooh, purple. You see, at the time, there weren't that many ways to make purple dye. In fact, the best way that it was done was really to isolate sea snails, crush them, grind them up, or mollusks of some kind, grind them up and extract molecules from them like Tyrian purple or indigo. You can read in the book of Acts about Lydia, a seller of purple, a businesswoman who helped Paul on his missionary journeys and was an early convert to the church. You can tell she was a successful small businesswoman because she sold something that was very expensive, which is purple dye. And this is why purple is a color that's associated with royalty in ancient times, because nobody else could afford it. Perkin changed all that because he made the color purple. And so he was a shrewd businessman. He was like, let's see if this can dye fabrics and textiles. It worked. He opened a factory in 1857. He made this discovery when he was 19, and by the time he was 36, he retired a wealthy man, and his name is still associated with the British Royal Society of Chemistry and also with prominent awards in chemistry because of this achievement. The molecule he made is called movine. It's actually a mixture of molecules. I will show you the structure, and you can see that it's quite complicated. There are a lot of aromatic rings. I've highlighted the portions that come from each one of his three starting materials. The ortho substituted is in purple, the aniline is in orange, and the para substituted is in green. This is one of the mixture of molecules that he made. He didn't know it at the time, but modern analytical methods have been able to figure out what the structures are. One of the reasons it's colorful is because it is so highly conjugated. We talked about this a long time ago when we talked about how you see, right? When the way you see is the molecule that absorbs light in your eyes has a gap between HOMO and LUMO that's in the visible range. Same thing with dyes. They have gaps between HOMO and LUMO where a photon of visible light can excite from HOMO to LUMO, and that photon gets absorbed, others get reflected, and then the molecule appears colorful. But this really, aside from his economic success, it led to a surge in interest, especially in Germany, into research into generating dyes, perfumes, anesthetics, inks, drugs, by making interesting molecules. And the idea of chemotherapy really was born not too long after this discovery. Here are some other dye molecules that became important. These are different from Perkins. These are called azo compounds, and they share the feature of having a nitrogen-nitrogen double bond in the middle that connects two separate parts of the molecule. The azo molecules are also highly colorful dyes, and they are much easier to make than Perkins movine, and they are easier to vary. So you can see, if I could figure out an efficient way to make this connection, I could independently vary the two rings on either side, and maybe I could generate dyes with different colors. And that's exactly what the scientists did. You can see them doing this with this even more complicated red dye in which there's something in the middle, two azo groups, and then different groups on either side. So this led to a surge in people just making dyes for various purposes. Along the way, they started to use the dyes to stain cell samples, because if you've ever looked at a cell under a microscope in visible light, cells are basically transparent and it's hard to see what's inside the cell other than squiggly lines. If you use certain dyes, they will get taken up by certain subcellular organelles more than others, and suddenly there's some contrast and you can see the inside of the cell. About that time, a German chemist and biologist, Paul Ehrlich, was using this dye, methylene blue, to stain cells, and he had this idea, if it gets taken up by cells, maybe I can use it as a drug to kill cells that I don't want to be alive. And it actually worked to kill a plasmodium parasite. And thus the idea of a targeted molecule that kills a specific cell was born, and we're still using that idea with modern day cancer chemotherapy. So I'll have more to say about that a little bit later. What we're going to learn next time is how to make molecules like this. All right, good luck on the exam. I'll see you Friday.